Hey, Dr. Clark here as always, and in this video we're going to be learning about the fundamental theorem of line integrals. I'm going to break this up into 3 separate videos, I think, showing doing some examples and then some new ideas, and then examples and new ideas kind of spread out. So hopefully that is helpful for you. But let's jump into the first idea. So fundamental theorem of line integrals is where we're going to head, but we've got some places to go along the way. And the first stop on the road is going to be vector fields and potential functions. So the key question here is, does every vector field come from a potential function? And to get us there, we need to remember Clairaut's theorem. So Clairaut's theorem said that if you had a function f, little f, and you took the mixed partial derivatives fxy and fyx, that those would actually be equal to each other. They're not the same thing mathematically, but when you work them out, they will always end up matching up as long as f is a nice function. And that will end up answering our question above. So how does that answer the question above? Well, if f is a vector field and for some little function f, the gradient of little f is equal to big F, right? So if the vector field f comes as the gradient of that little function, the components of the vector field would be the derivatives of f. It would be fx, fy, fz, right? But then you could take more derivatives of those components, and the mixed partial derivatives would have to match up by Clairaut's theorem. So for example, let's take the vector field 1x, and you'd want to say, hey, could this thing be the gradient of some function f? Right? Is it possible for the vector field 1x to be the gradient of some function f? Well, if it were, the 1 would have to be the x derivative of f, and the x would have to be the y derivative of f. Well, if the x derivative of f is 1, then the xy derivative would be 0, because 1's derivative with respect to x, or y, would be 0. But if x is the y derivative, then fyx would be 1, because the x derivative of fy would be 1. But 0 doesn't equal 1. And so if Clairaut's theorem is going to be true, it just can't be, right? There's just no way for 1x to be the gradient of some function f. So there you go. It turns out that not every vector field is the gradient of some potential function f, and because of that, we give the name conservative to vector fields that do have that property. So when something is special, you give it a name. So a vector field f is called conservative on a region if there exists some function f. We call that the potential function, such that the vector field f is the gradient of that function on that region. Okay, so now we've got a term for, there's conservative vector fields that come as the gradient of some potential function, and then there's non-conservative vector fields. There's 2 kinds of vector fields, essentially. All right. Well, now you might want to know, well, how do you know if one is one or the other? And that comes as this test for conservative vector fields. So Clairaut's theorem basically gives us the ingredients we need to find how to test this. So if the vector field is PQR, and you want to know, does this thing come as the gradient of some little function f? Well, then P must be the x derivative of that function f, and Q must be the y derivative. And so Py should equal Qx. And Qz should equal Ry, and Pz should equal Rx. So that's what these conditions are. If it's a 2-dimensional vector field just with P and Q, then there's just the one condition, Py has to equal Qx. So basically, Py would be fxy and Qx would be fyx, and they would have to match up if there was some little f whose gradient was the vector field f. Okay, so that's the test for conservative vector fields, and we've got one example for you here to kind of see, like, okay, here's some random vector field. You want to know, is this thing conservative, and if so, is there a function f whose gradient is equal to the vector field f? Okay. Well, if the gradient of f was equal to capital F, then the x derivative of f would have to equal x plus yz. The y derivative would have to be y plus xz. And so fxy would be what? Fxy would be z. And fyx would also be z. Hey, those match up. Good. Okay. Then fx is that, fz is that, z plus xy would be fz. So if we do fxz and fzx, fxz would be y, fzx would be y. They match up. Check. And then let's try these ones. Fy would be this, and fz would be this. So fyz and fzy would both be x. That checks out. And it turns out you can see that f of xyz equals xyz plus x squared over 2 plus y squared over 2 plus z squared over 2 plus 7 is in fact a potential function for this vector field f. Because if you take the gradient of this, you're going to get exactly this vector field right there. And so that's kind of how you can check. And in the next video, we're going to see where do you come up with the potential function. So stay tuned in the next video, and we'll show you how to do that.